Ajá. Ok, emitir. Buenas tardes a todos. Vamos a iniciar con el coloquio del Instituto de Física de la UNAM de hoy, que será impartido por el profesor Patrick Maley de la Universidad de Notre Dame. Antes de empezar, le cederé la palabra al doctor Javier Miranda, que en representación de la directora nos dirá unas palabras. Adelante, Javier.
Bueno, ¿sí me escuchan?
Sí.
Sí, bueno, buenas tardes. Good afternoon. Quiero, bueno, desde luego dar la bienvenida a todos los asistentes de manera remota, desde luego, a este coloquio del Instituto de Física. Y en primer lugar, a nombre de la doctora Cecilia Nogués, nuestra directora, ofrecerles una disculpa porque en este momento ella se encuentra en una reunión, según entiendo, con algunos funcionarios del gobierno y no va a ser posible que se conecte a tiempo de iniciar el coloquio. Yes, I am explaining to all the attendants that our director, Dr. Cecilia Nogués, is presenting her apologies because she is right now attending another meeting with some government officers, and so she will try to connect later to the colloquium. But anyway, we in the name of the Institute, we thank you for accepting our invitation, and I will give the microphone again to Luis to make a presentation. Thank you.
Thank you, Javier. Well, first to start, well, I was some way select to present and say something about Professor Maley. Since I had the opportunity to work, well, really recent 2 years ago in a very nice and successful experiment with him at this very nice facility of Notre Dame. So let me start with a short review of Professor Maley. He did his undergraduate studies at Tennessee Technological University, graduating summa cum laude in cursus honorum. And he attended graduate schools at Rutgers University, where he received the Stewardship Science Graduate Fellowship from the National Nuclear Security Administration in the Department of Energy. After Cruz's work was complete, he was stationed at Oak Ridge National Laboratory, where he did his dissertation work at the Holyfield Radioactive Ion Beam Facility. After he graduated from Rutgers in spring 2012 and spent 2 years at the Colorado School of Mines as a postdoc, leading local research efforts at Triumph, this main facility of Canada, on both big arrays known as Tigris and Dragon. In the spring of 2014, he went to the University of Notre Dame as a postdoc, where he participated in the planeful scientific efforts with TwinSol, this main facility, which he's going to talk today. And in January 2018, he was converted to assistant professor of research, where he took over research management of this big facility of exotic nuclei called TwinSol, with more than 130 publications in specialized journals and more than 700 citations. We have now here to Professor Patrick Maley. Patrick, please start. You need to share or some presentation or so.
everyone can see?
Yeah, now we can. Thank you very much.
Originally, I had planned to, when I was asked to give this talk, to talk about the give a general overview of the nuclear science we do with TwinSol at Notre Dame. But as I started writing the talk and putting my slides together, I realized that I wasn't really able to do any one subject justice because there's just so much that we do here. So in the end, I decided to kind of focus on one aspect of our research efforts over the last few years. That's taken up about half of our time, really. So I'm going to talk to you about how we've been testing the standard model at Notre Dame. Now, okay, what is the standard model? Now, briefly, it's sort of a collection of a theory that explains the elementary particles as we understand them and the elementary forces that govern interactions between them. And this includes, three quark generations, or generations of leptons, various gauge bosons for the interactions, and it very accurately predicted the existence of the Higgs boson. Now, at this point, you ask yourself, well, what else is there to do? And one of my favorite quotes is from Lord Kelvin back in the early 20th century. There is nothing new to be done with physics now. All that remains is more and more precise measurements, which is how a lot of people sometimes view nuclear physics, but we, of course, know that's not necessarily the case. Now, as we know, the standard model does have some issues. For example, we've got these gauge bosons, which govern the interactions or carry the interactions between the elementary particles. We've got the electromagnetic force, the weak force, the strong force, but there's no theory of gravity. We have no explanation of gravity, how it interacts, where it's coming from. And of course, there's a number of other issues. There's no description or explanation of dark matter, what it is or how it interacts, what happened to the antimatter. We know in the very early times of the universe, there was a balance between matter and antimatter. And then something mysterious happened, and now most of the antimatter just went away, and we're left with primarily matter, which is great for us because otherwise we just wouldn't exist. But what happened to that antimatter? And why are there only 3 generations of quarks and leptons? And what determines their mass scales as they are? So there's different ways people go about testing the standard model. In some instances, they look for this electric dipole moment. And if it's big enough, that could be some evidence for CP violation. Many groups are looking for the ever-evasive neutrinoless double beta decay, which would signify that lepton number is not actually conserved and would help show that neutrinos have mass. And of course, there's always these dark matter questions. And many groups have started actually trying to provide theories to use dark matter to explain some of the anomalies we see in nuclear data. But our efforts at Notre Dame have been in using these precision beta decay measurements in order to help test the Kabibo, Kobayashi, Maskawa, the CKM matrix unitarity. Now, what is the CKM matrix? Now, the CKM matrix basically governs the interactions between the quarks. There's always some probability that one quark could transform into another quark flavor, and the matrix elements of the CKM matrix sort of give the probability of such an interaction occurring. The way it's set up, when we talk about unitarity, if we took the squares of a single row of elements, those should, in theory, add up to 1, because that would signify that the theory has completely encompassed all the possible channels that could be open for this. Now, what would non-unitarity even signify? Well, perhaps there's other quarks. Maybe there's a 4th generation of quarks. Maybe we'll end up with the left-right quarks, which I think would add a nice kind of symmetry to the system, which means there'd be another possible row or column, I guess, in the CKM matrix. Or maybe there's some other new physics, some exotic physics we don't entirely understand. Or also very possible there's some problem with experimental data or the theoretical corrections we use in our models. So for the last 10, 20 years, there's really been a big push internationally to kind of really constrain the CKM matrix elements to test its unitarity. Right. And of course, the biggest element that we've been paying attention to is the VUD. So that's the interaction between the up and down quarks. Naturally, obviously, because up and down quarks kind of compose most of the nuclear matter that we know of. Now, how do we use beta decay to study VUD? Well, if you take your kind of typical beta decay spectrum, assuming a very pure source material, you end up with this nice kind of, on a log plot, we end up with this nice linear line. It's governed very simply by this relation where lambda sort of gives you like your decay rate for your lifetime. But we also know that this obeys Fermi's golden rule, the decay rate does. So, but again, how do we use this to get VUD? Well, this M parameter is a matrix element. It actually carries the information of the interaction that we're interested in studying. Now, in its pure form, is a somewhat complicated function, but in the cases of superallowed pure Fermi beta decay, and I'll explain more about that here in a minute, you can simplify this matrix element very greatly to just being a calculable term times this VUD, the thing we're actually looking for. Now, in the last slide, I mentioned this superallowed pure Fermi beta decays, and I know there might be some in the audience who don't actually understand the difference between Fermi to Gamow-Teller transitions. I just want to spend a little time kind of going over that. When we're talking about transitions, we talk about allowed transitions. Those are the most probable ones. Here we're assuming the electrons and neutrinos, or the antineutrinos, are created at the center of the nucleus. So if they're at the center of the nucleus, the radius for their position is 0, so they can't actually carry any orbital angular momentum. So any changes that occur to the angular momentum of the system have to come from the alignment of the spins of the outgoing particles, the electron and the neutrino. In the case of if the spins are anti-aligned, so that they cancel, we know the change of momentum would be 0. We call this a Fermi decay. When the spins are aligned, the change of momentum could be 1. We call that a Gamow-Teller decay. And I've just got a few examples here. In the case of 14 oxygen, when it beta decays to the excited state of nitrogen 14, that's a pure Fermi decay, because only the J equals 0, delta J equals 0 is the possible interaction. In the case of helium-6, when it beta decays to lithium-6, you end up with a change of momentum of 1 always. So that's a pure Gamow-Teller decay. However, there are situations like when the neutron decays to the proton, in which the mixing could either be 0 or 1, depending on how the spins align. And we call this a mixed transition, and that'll something to keep in mind for later. Excuse me. Now, so we've talked about this M parameter, and that this matrix element gets us links us to VUD in the beta decay. But we've also got this other rho term. Now, this term is it's a phase factor. It carries a lot of the kinematic information from the decay, masses, energies, angular momentums, things like that. And so we're able to express this. And we know that the lambda, the decay term, can also be related to the partial half-life for this particular decay branch. So here we're relating this matrix element, which has the VUD, a bunch of constant terms, and then this F function here. Now this is something called the Fermi integral. And essentially that's entirely determined, governed by the Q value of the beta decay. So just the difference in the masses from the mother to the daughter. So here, if we just rearrange things, group all of our constants together in just one constant term, like we nuclear physicists like to do, you end up with a relatively simple form relating the FT value to VUD. And but this is, again, this is for exclusively for superallowed pure Fermi beta decays. All right. Now, just looking at this a little more closely, we've got our FT values. This function is dependent upon the Q value. We've got our half-lives. We've also got this term here, which involves the branching ratios and electron capture fractions. Then we've also got the VUD, which is the thing we want. So what are the next steps? All right. So what we would like to do as physicists, we'd like to measure FT for many measurements of the FT value by using many nuclei. And then they should, theoretically, if they're constant, we can use those values to extract a value for VUD, or extract a value for FT, which would then we could use to extract a value for VUD. Now, for many pure Fermi transitions, this has actually been tried. The first look at the data from a few years ago, we see that there does seem to be almost a trend, like it's almost flat, but as we increase in mass, you see there's definitely a trend upwards in this FT value. There was some discussion as to what could be going on. And so we figured out that there actually needs to be a number of correction terms in this. For example, one of the assumptions we make when we simplify the matrix element, the M matrix element, is that there's isospin symmetry. That is to say that as far as the nuclear force is concerned, a proton and a neutron are perfectly interchangeable. However, in reality, we know that's not necessarily the case because the proton has charge and it's going to interact differently to the nuclear charge distribution than the neutron would. So there has to be some kind of correction term for that. And there's also some correction terms that are related to the models we use to describe the radiative processes. In the end, we're able to group these, and we're able to get a relatively simpler, slightly more complicated form for our FT value, where we've got what we had before, plus this small correction term. Now, if we go back to that plot and we implement our correction terms, we see that the FT values for all these nuclear actually align very nicely, much better than they were before. And so because the FT value seems to be constant as a function of mass, or Z, we can now extract VUD, which was done relatively recently by John Hardy's group. And so now that we have a measure for VUD, we can test CKA matrix unitarity, which they did. It came up with the value, this value here, which if you can look at the uncertainty, you see that it's not actually as inconsistent with unitarity. In fact, it's different by almost 2.5 sigma, which is fairly significant. So that's exciting and interesting. But of course, this is just one avenue to determine VUD. And since we've got this interesting result, as physicists, we know the next thing we need to do is try to verify this result somehow. So there's different ways we could go about obtaining VUD. The first thing we did was using these pure Fermi transitions. And we did that because it's the most precise determination. The FT, the function relating VUD to FT is simplest. The main downside is that you do actually still need nuclear corrections. We could look at pion decay because that's a relatively simple system. As such, it doesn't need any nuclear corrections. However, pions are experimentally just a challenging thing to study, and the branching ratio is fairly low. Neutrons would be an obvious choice to study the decay of and extract VUD, but there are certain issues with the neutron half-life, as many of us know. Until we can agree on what the half-life is, it's hard for us to progress with using it to extract VUD. And we still also need to know this Fermi gamma-Teller mixing ratio. I'll explain more about that in a minute. The other option for us is actually look at nuclear mirrors. So there are other nuclei that would decay, that would beta decay into their mirror nucleus through a mixed transition. That's a mixed Fermi to gamma-Teller mixed transition. From that, we could also extract VUD. And that's the route that most people who were studying this have gone. So getting VUD from mirror transitions is, as I mentioned, a little more complicated. You have the function we had before relating FT to VUD and the correction term. However, there's this additional term here with this rho parameter. Now, what that rho is since it's no longer a pure Fermi transition, we've got a mixing between the gamma-Teller and pure Fermi transitions. And so we have to understand what the mixing between these two possible transitions is. That's what this rho parameter tells us. Unfortunately, it's a very difficult thing to measure, and for many nuclei, it's only been measured for up to 5 nuclei right now. And because the data is so uncertain, currently the VUD that we can get from these interactions is much less precise, almost 7 times less precise than we get from the pure Fermi transitions. So there's been a lot of experimental work done to try to refine all of these values so that we can get a better determination for VUD from mirror transitions to sort of verify the results that we're getting from the pure Fermi transitions. In particular, at Notre Dame, we've been focusing on measuring the half-life and determining this somewhat elusive Fermi to gamma-Teller ratio, but I'll talk more about that later in this talk. Now, what I've got here essentially is a plot of the relative uncertainties of the FT value from mirror decays, mixed mirror decays, as a function of mass. Just to kind of explain, the green bars would represent the relative contribution to the uncertainty from the Q values. The red lines represent half-lives, blue the branching ratios, and then we've got these smaller nuclear term corrections. And if you notice, this plot's from a few years ago. In many cases, in most cases, the half-life is actually the largest contributor to the uncertainty. And half-lives, especially for nuclei that are relatively close to stability, should, in theory, be a fairly straightforward thing for us to measure. So it seems like a natural avenue for us to focus experimental efforts on. And which is something we've been attempting to do at Notre Dame. Now, at Notre Dame, we've got the Nuclear Science Laboratory. It's been around for forever, as far as I'm concerned. It's almost 90 years old now, I think, or maybe just over 90. And currently, this lab has grown a lot in the last few years, and we actually currently have 3 particle accelerators that are in use. The smallest one, this 9S accelerator, is a little 3 megavolt machine, which delivers high-intensity protons and alpha beams to these applied physics setups. And they mostly do things like PIXI, where you use proton excitation to survey materials and try to figure out what's inside. We've got a 5 megavolt kind of Taylor accelerator here, which has been optimized to create very high-intensity, low-energy beams of protons or alphas for nuclear astrophysics studies. So in a lot of stellar environments, what you really want are low-energy protons and alphas for a lot of your studies. So its efforts are primarily focused on nuclear astrophysics. However, the workhorse for a lot of our programs at Notre Dame is this 10 megavolt tandem accelerator, which is supported by 2 ion sources, a multi-cathode cesium sputter source, and then a helium ion source. And they do provide beams to various setups. We've got an AMS magnet. We're installing an INGI split pole here. We've got a few multi-purpose detection setups, and of course, TwinSol, which is where I spend most of my days, which is our radioactive ion beam producing apparatus. From TwinSol, we then deposit our radioactive beams into our experimental setups, where in particular, for this talk, that would be the beta counter and the ion trap, which we plan for the future. Now, TwinSol is one of the oldest radioactive ion beam producing facilities around. It's one of the original, the Big Sol, which was the predecessor to TwinSol, was actually one of the original radioactive ion beam facilities. And it's a relatively straightforward setup. Consists of 2 coupled 6 Tesla superconducting solenoids. The primary stable beam is provided by that 10 megavolt tandem I showed you in the last slide. And then here we bombard a production target, which consists of either various solid targets, could be beryllium or carbon-13, and in many cases, and in the case of this talk, it was a deuterium gas cell. Now, from the deuterium gas, like, for example, one of the data I'll be discussing briefly next is beta decay of 33 chlorine. And in this instance, we bombard our deuterium gas cell with a 32 sulfur, and we transfer a proton to the sulfur to make our 33 chlorine. However, there are, of course, other reaction channels that could be opened, and so we have to have a way of separating everything. The contaminants from the thing we're actually interested in, and that's essentially what TwinSol is trying to do. Okay, so the first solenoid collects the outgoing fragments from the production target and focuses it through a variable aperture crossover point. Second magnet then collects the outgoing particles and focuses them to our secondary target location. Now, just in the last few years since I've been there, TwinSol has really grown a lot. Currently, we've produced radioactive beams all the way from actually down to 8 lithium and 7 beryllium, 10 boron, and all the way up to actually 41 scandium. So something we did just last year before COVID shut everything down. As far as the local professors who support this program go, they're sort of broken into 3 different distinct research focuses. Professor Tan An often or primarily studies alpha clustering in nuclei, essentially how much a nucleus acts like a group of alpha particles. Professor Bardian primarily studies nuclear astrophysics, specifically nucleosynthesis. So he studies a lot of reactions that will help shed light on various nucleosynthesis environments like nova or just stellar burning, normal stellar burning. Professor Berdeur, who kind of motivates this talk, studies the weak interaction of mirror transitions. But of course, as many people in this talk, like Lewis and Ellie know, we do a variety of other research studies too. Now, again, we're measuring half-lives. So as I said before, half-lives should be pretty easy, right? There shouldn't be any problems. Well, it turns out it's more complicated than we thought. What I've got here is sort of explaining why certainties are as high as they are for extracting VUD from mirror transitions. Here I've got the plot of the fluorine-17 half-life as a function of time for the last 50 years or so. And you can see just how much the half-life varied over time, which is a little confusing. So when we first started this effort, we went back and we're really looking at the old data and came up with the primary reasons why these data might disagree so dramatically. In many instances, contaminants in the radioactive decays weren't properly accounted for. Some of the older analysis that was done was just, the techniques were very simplified, and certain effects were not accounted for. There has not been, oftentimes, they don't do a lot of efforts to study the systematic effects of things like detector voltages and thresholds could impact the data. And in many instances, they don't actually try to really characterize the background in their data before trying to get a precise determination for the half-life. So these are sort of the things we keep in mind as we try to plan our own program to study half-lives. So in the end, we created a relatively simple setup. We have this rotating target wheel. We implant our radioactive beams that we make with TwinSol into this gold foil. Gold, obviously, because it's got a very high Z, and at these energies, we're extremely unlikely to excite anything or activate anything in gold that way. And it's also relatively easy to get pure. So we implant on our gold foil, which is actually usually sitting over here during the implantation, for 3 half-lives, because that's about how long it takes to saturate to get to where the amount of decay is equal to the amount of ions coming in. We cut off the beam, and then we rotate over here to our beta counter. That's a little simple plastic scintillator backed by a PMT, and we count for 20 half-lives. Now we rotate away so that any kind of beam activation will be insensitive to any kind of beam activation that could be occurring from over here, and it helps minimize our background. Now, as I said, we count for 20 half-lives, and we do that so that we're essentially looking to decay to background, because we really want to measure that background as well as we can. In addition, a lot of times there are long-lived contaminants which you don't notice until you're getting down, until most of the thing you're interested in is fully decayed away. So we count for 20 half-lives to really try to understand all the features in our data. And then we rotate back to the primary implantation position, and we just do it all again. Now, as I said, one of the things we try to do here is we try to spend a lot of time to carefully study the systematic effects on the data. We vary things like the PMT bias voltage, discriminator thresholds, implantation times, implantation rates. We do all this to try to help us understand the nature of any kind of background materials we might be seeing in our data, and to understand how these effects impact the half-life that we determine. Now, as I mentioned earlier, identifying contaminants is one of the primary challenges in these kind of measurements. One of the most straightforward ways to do this, of course, is through particle ID. So we have 2 different detector systems that we use to try to help us with this. Ion chambers, just a little gas ionization chamber, and silicon detector telescopes that compare the energy loss in a small region of the material and compare it to the total energy of the particle. Because the energy loss in a region is very sensitive to the charge, the mass, and the energy of that particle. So from this, we're able to identify the majority of things that occur in our beam. Now, whether or not we use an ion chamber or a silicon telescope often depends on the energy. As many of you are probably aware, silicon detector telescopes can be a little tricky if you're running really low energy beams. But the flip side of that is silicon telescopes tend to be a much cleaner, much nicer looking spectrum. And from this, we can help identify things that could be in the beam other than the thing we're interested in. And also, in many instances, we can also use gamma rays to identify possible contaminants by just looking at gamma rays coming off of the implantation. That gets a little harder though, because in many instances, the many things that could provide backgrounds don't have characteristic gamma rays for us to identify, and they would have to be abundant enough in the implantation to show up above background. So one of the ways you can help identify contaminants or the existence of contaminants is by actually looking at the data itself and using careful analysis techniques. This plot might look a little funny, but it's actually just, I mentioned before that we go through several iterations of measuring the half-life at the same settings just many times. And what I've basically done here is plotted the half-life for that 33 chlorine data for one set of settings for each iteration. And you're sort of seeing it coming down to different backgrounds. And the fit here is just an average fit over the course of the data. One of the things you'll notice here is that the fit for the background levels tend to really estimate what we expect the background to be. One of the things we can also do is plot the residuals. So we subtract the data from the fit essentially and plot it as a function of time to see how it varies. If you look carefully, and I'm hoping it shows up in your screens, these dotted lines have a definite downward trend here, which suggests to us that there is a contaminant in the data that wasn't accounted for yet. So one of the ways we can do this is just by adding a freely floating parameter where we let the ratio and the half-life just very freely. And that gives us a much better fit, and our residuals plot flattens out nicely. But we don't necessarily have a good measure of the half-life. And in this instance, the half-life that we extract could be something as light as oxygen 15 or as heavy as fluorine 30. But we can't identify it more precisely than that because the data is so sparse on that. So we need to try, and without knowing the half-life, it makes it harder to get a precise value for the chlorine 33 half-life. Another way we can look for contaminants is by using something called a chop plot. Now, the chop plot, we essentially take our decay data, we cut off the first second or two of the data, we measure the half-life, and then we cut off the next second or two of data, measure the or calculate the half-life again from our data, and we keep doing this until we essentially cut out all of our data. You'll see here for the first 20-25 seconds, the half-life essentially is constant as we cut out. That means that there's at this region, the data is very well, essentially just pure 33 chlorine decay. The half-life for chlorine 33 is about 2 seconds. But once after 10 half-lives, when the chlorine is essentially all decayed away, you see that the half-life starts to immediately rise from our chop plot, which suggests that there is some kind of long-lived contaminant. Again, this tells us there's a contaminant in there, but this doesn't necessarily help us identify it. So one of the things we can do is just try to use logic. So we go to NMDC and we put it in our reaction calculator and just see the different kinds of, with our beam and our target, what are the different reaction channels that are probably open to us. One thing we can do right away is draw, this red line represents our kinematic threshold. So we are running about 57 MeV. So I know anything below this line was energetically forbidden for us. So I don't have to worry about 26 aluminum. Most of these can immediately, most of these can immediately get tossed away, like the 32 sulfur, 33 sulfur, because these are stable. So they would not create any kind of radioactive contaminant for us to notice. We see that still leaves us with 32 phosphor, which isn't energetically possible, even though the Q value is very negative. However, the half-life of 32 phosphor is 14.5 days. So since we're only counting for about 30 seconds, we're very unlikely to see much effect from 32 phosphor in our data, so we can mark it out. It sort of leaves us with 34 chlorine, a capture reaction, but at our rates and our energies, we're very unlikely to get much of any impact from that. So it turns out what we're most likely seeing in our data is actually just 30 phosphor. So from that, I can then use that to fix the half-life for my radioactive contaminant, and thereby to get a more precise determination for my 33 chlorine. Now, this data at this point is still still ongoing. I still need to study the systematic effects to everything. But at this point, I just wanted to show that there was a relatively recent measurement from Ganil. Right now, our uncertainty is about on the order of the Ganil measurement, which might not seem statistically interesting, except that it still does significantly improve the world average value for the 33 chlorine half-life. which is sorely needed. And so our program as a whole, this is sort of showing, I specifically talked about the 33 chlorine here, but we've done this for 6 different nuclei so far. 3 have been published. Actually, we've done it for 7, I guess. 4 are still under analysis. But I also wanted to point out how many other institutions are also contributing to this effort. We've got Neil, Texas A&M, Evascula, which is mostly measuring branching ratios. I know there's a group or 2 at Triumph that's interested in measuring, minimizing the Q values of the 13 nitrogen, 15 oxygen for those contributions. So this effort to extract VUD from beer transitions is very much a huge international effort that's been ongoing. Now, of course, all this is just to extract FT, right? What we want in the end is VUD. Now, again, here's our plot of FT. And as I mentioned before, what we're measuring here is FT, but what we really need is VUD. And so to get that, we need to measure this rho, this Fermi to Gemma-Teller mixing ratio. Now, how do we do that? There's different ways to get rho. You could look at the betas and the neutrino asymmetry parameters, but it turns out that the most sensitivity you'll have to it is through this beta-neutrino angular correlation parameter. So that if you want to get a good measure for this rho, that's the most sensitive avenue for us to take. Now, measuring neutrinos is notoriously difficult. They don't interact much, if at all. Usually you need very large scale detector systems in order to do this. So measuring the angular correlation between the beta particle and the neutrino is very hard. So what we can do is go the other route. We can try to do a full kinematic reconstruction of the event using something called a Paul trap. Now what the Paul trap does is it takes a grouped bunch of radioactive particles of the substance you're looking for, like in this case 33 chlorine, and it magnetically confines them in a small region. And we sit there and wait for the beta decay. Now the beta particle will go one way. When the beta particle goes one way into our position sensitive detector, backed by a scintillator, we're able to measure the energy fairly precisely and the position. So that gives us the angle of that beta particle. The ion we call going the opposite direction. It gets detected by MCP array, a position sensitive MCP. Which gives us the angle, and we can use the relative timing from the beta and the ion to give us a time of flight for that heavy ion, which gives us the energy. So now we've got angle and energy for the beta and the ion, which allows us to extrapolate the angle that the neutrino came out of. And from that, we could then do a full, could extract this correlation parameter, angular correlation parameter. So at Notre Dame, we've got an MRI approved and funded to build a Paul trap to do this at Notre Dame. And that's one of my favorite acronyms I think I've seen. We're creating St. Benedict, the Superallowed Transitions Beta-Neutrino Decay Ion Coincidence Trap. That was just creating an acronym was an enormous effort by one of our grad students, and he was very, very proud of it. Now, with this, we can take our TwinSol beams, which are relatively intense and clean for the beams that we make. In many instances, it's much better to do it someplace like here, where time of these measurements can be, time is more generous. If we need to do a 2-week measurement of something that's relatively straightforward to do here, then it would be somewhere like at the NACL. And so we were planning to build this here. Now, it's primarily broken down into 4 big components. Now, the first part is the gas catcher. This we're actually getting from argon. What it does is it captures the radioactive ion beams from TwinSol and thermalizes them in helium gas. We have an RF carpet that sort of applies across the edges that forces the ions to drift towards an exit point, where it goes through a 1 millimeter aperture, which ejects the ions in a kind of a gas jet, which gives it the momentum it needs to kind of traverse through the rest of the system. And again, this is a gas catcher we're getting from argon that's been decommissioned from their when they upgraded their system. Now, this is the part of our setup that's the most fluid right now. We're still sort of designing how we want this exactly to happen. But currently, what we are planning on is having this tiny aperture through with an RF carpet across it, which will help our ions come out straight and focused with enough energy to transport them to the cooler buncher. And it's going to be composed, probably playing on a SPIG sort of setup where we've got these 4 rods that go through, and we apply an RF across them to sort of help keep the ions focused as they drift through. The cooler buncher is does a lot of the work for preparing the ions for injection to the Paul trap. What it does, like many bunchers, it thermalizes, in many cases almost stops the ions, allowing them to group up to a saturation point and then get dumped into the Paul trap. The cooler buncher we're using was primarily inspired by the one in use at NACL. So there was a collaborative effort between Argonne National Lab, the NACL, and Notre Dame to build several of these for different groups. And this one is ours. Now, it's been built, it's at Notre Dame. We are currently testing it and actually commissioning it with a little mini ion source just to characterize its transmission. Finally, we've got the Paul trap. And on this part, we haven't started building yet, but we've started looking at getting quotes for the different components of the system. Like the Paul trap I showed before, we've got DSSD silicon detector to get position for the electron. We haven't yet decided if we're going to back it by a couple of thick silicon detectors or just use a scintillator. I think we're leaning towards the thick silicon detectors in the end, just for the improved resolution. And we'll have 2 arms of that rather than just the one. And then the other 2 arms, again, will have our position sensitive MCP, which will give us the time of flight of the recoil atom and position. But again, these designs are currently being finalized by one of our grad students, and we're hoping to start building this relatively soon. Now, actually, that's pretty much all I had today, just to kind of conclude and wrap up my talk. So we talked about the superallowed pure Fermi transitions as the most precise means for extracting VUD. This has been done, and currently, as of a paper as of just a few months ago, we see that the CK matrix does violate unitarity. So there's been a large global effort in the world to extract VUD from mixed mirror decay transitions, provide us confirmation of this interesting result. At Notre Dame, many half-lives that are currently dominating the uncertainties in extracting VUD from mixed mirror decays have been measured, and some of them have been published. The rest of the data is still being finalized. But even then, one of the main parameter we need to go further is this Fermi-Taylor mixing ratio. And so at Notre Dame, we're building a new ion trap called Beta-Dict, which will be linked up to TwinSol, and that'll eventually hopefully help us measure this elusive parameter. I'd like to thank my collaborators, in particular Dan Burdett and Maxime Berdure, who helped me let me shamelessly steal many slides for this talk. Questions?
Thank you very much, Patrick, for this nice seminar and to show all the beautiful things that you have there at Notre Dame. We can start with questions and comments. You can just raise your hand or simply try to start to speak, please. Ephraim, please.
Well, thank you for the very, very nice talk. Congratulations on the very, very, very nice results on the lifetime measurements of these radioactive nuclei. You mentioned that this would be the most stringent test to the VUD matrix element. Which would be the closest different approach to measure that matrix element that would be competitive with you with this technique?
I don't trying to understand the question. So.
Oh, okay. So there are many different approaches to measure this matrix element.
Right.
Like you mentioned also neutrons, neutron decays, electric dipole moment, and there's also these proton delayed beta decay experiments. So which one do you think is the most competitive with what you're doing?
Those are the electric dipole moments and the neutrino self-repeated decay won't necessarily measure CKM. They will help test the standard model, like for example, the neutrinoless double beta decay will show that there is lepton number violation, which could be very interesting. But I wouldn't necessarily put a lot of, I would not put my bet on neutrinoless double beta decay as finding anything particularly interesting yet, because it's the lifetime of this is the age of the universe, and it's just very difficult to try to experimentally statistically measure these things. Now, VUD, the most precise value you can get, as I mentioned earlier, is just from looking at these pure Fermi transitions. And they did, and they got a very nice value for VUD and showed that it was not unitary. But we need to confirm that. And so let's go back a bit. You could also use neutron or pion decays, but experimentally they provide their own challenges. Pions because it's just experimentally more difficult thing to do. Neutrons because we can't seem to agree on what the half-life of neutron actually is. So that's one of the main limiting factors there. So nuclear mirrors provide a nice likely avenue for us to do it. It also allows us to extract FT using many different measurements, which I think would be more precise. And so with FT, we can then get VUD.
Nice, thank you.
Thanks, Efrain. Eli Aguilera, please. Switch on.
Yeah, can you hear me?
Yes.
Patrick, thank you for the nice update of all these great things that you are doing at Notre Dame. Some of them I really didn't have an idea that you do there. So thank you. My question is related to the background that it is an important correction that you have to do in measuring lifetimes. You mentioned, for example, in the case of chlorine 33, you look for contaminants and corrected for the half-lives of those. I wonder if you also have some background from the environment. Is that taken into account?
There's, let me go back. So there's another parameter I didn't talk about here, B, for our background. That's our constant background, which is pretty small. The original detector we used had a very high dark current, so our background then was very high. So we ended up buying a new PMT, which had a very low dark current. So therefore, our background ended up going down to about half a particle per second, even when we bottomed out our thresholds. So, but still, understanding that background, which doesn't seem like a lot, it really fixes the tail of this distribution, which has a surprisingly large impact on the actual precision of your half-life measurement, which I was very unaware of until we started doing this.
Okay, thank you.
Libertad, please.
Okay. Hi, thank you very much for this very nice talk. It's very interesting to learn about. I work on neutron physics, and it's very interesting to see these different approaches to find.
You could tell me why the half-lives don't agree?
Yeah, we don't know, but yeah, many people are still working on that. I'm not working directly on half-life, but I'm working on NAB, the neutron beta decay, the correlation parameters. But you mentioned that there is now recent work that seems to point that towards the violation of unitarity in the CKM matrix. Can you maybe comment a little bit more on that? Is this on the same unitarity test for VUD? Is that what?
So this was, last year there was a paper that came out that was sort of suggesting that there was I don't remember if it was last year or the year before now. 2020 is just a blur in my mind. But recently there was another paper that suggested that there actually was agreement with unitarity. But then John Hardy went through and implemented some more corrections and the most recent data, and was able to show, get a more precise measure for VUD, which, as we can see here, did not agree with unitarity in the end by about 2.5 sigma. So that's, I don't know, to me, that was kind of exciting and interesting, but that's because I've been staring at this for the last few years.
Yeah.
So we'd like to go through and verify this.
That's really nice. Thank you.
Angel Sanchez.
Oh, yes. Well, thanks for your talk. It's a huge work that you did and you are willing to do in future. So really huge work. I have a question about the purity, that if I understood well, the impurities of your beam is an issue that you have to face. And I wonder if this idea that I have in mind that you talk, that the third, I mean, if you could improve these impurities by means of improving the optics of the beam, or maybe introducing this third solenoid, or...
Yep. So yes.
And then I have a second question, but first, please.
Sure. The third solenoid will certainly help improve our purity and our optics. Having a third solenoid will allow us to help filter contaminants in different ways. We're still exploring how we want to do that yet. According to Jim Collada, he's been doing a lot of least calculations for us to help model what our third solenoid would potentially do for us. And he's showing that we could get significant improvements in the purity if we want by having the third magnet. In many cases, it's not necessary to be pure enough, but for some of these, like the scandium, actually I think the 29 phosphor that data could really use a little more enhancement in the quality of the beam. So right now the data is, it's certainly an improvement over the existing data, but it's not at the level that we really need it to be.
Okay, and the second question is about well, the compromise between the intensity that you get and the impurities. I mean, would you say that you need more intensity, or you reach somehow saturation in terms of dead time and this and that you don't really want to go to higher intensities in the production of the ion of interest?
Sure. Now, one of the things we studied this early on, which we were thinking, as is the case in most kind of nuclear physics measurements, you want more rate. You always want more rate. Even if your dead time is 70%, you're gaining more data that way. But as it turns out, the uncertainty of your dead time is one of the biggest contributors to the uncertainty of the analysis. What you want to do is, even though in many instances we could have more rate than we had, just by turning up the primary beam, you don't want that, because it decreases your overall precision because it increases your dead time. Even though the dead time never gets worse than say 90%, that's still going to net a worse data set than if we just measured longer at a lower rate with less dead time. That was an effect that we didn't really appreciate when we first started doing this. But now, of course, we understand.
Okay. Thank you for your answer.
Thanks. Genaro?
Yeah. Thank you for your talk, Maley. I was wondering on the radiative corrections. I know that in the superallowed Fermi, the radiative corrections are very well under control. I was wondering if it is the case in the mixed systems that you were showing. Are the radiative corrections well controlled in that case? Because you have two systems and then the mixings and interference are tricky sometimes.
So the radiative correction terms are certainly going to have an impact, and probably in some cases need to be studied better. But right now, the biggest problems we're having with precision is in the actual just experimental data and measuring these half-lives and these branching ratios and these Q values. So while in some cases, especially in the higher masses, getting a better, it would be nice to have better correction terms. It's not really like the main effort, the main problem we're facing right now.
Oh, okay, I understand. understand that. I'm a theoretician, so I was wondering if it would be worth to take a look on the radiative corrections. Eventually, you will reach precision enough to worry about.
I mean, it's always worth looking at, right? Because at some point it will end up being the main issue that we struggle with. But and that was one of the last set of big changes that were made to the extraction of EUD from the pure Fermi decays. They kept working on these correction factors and were refining their calculations and estimates of these correction factors, which is why at one point we thought we were agreeing with unitarity, and now with the more refined calculations, we're seeing that we don't actually agree with unitarity. So I guess yes, to me it would make sense to work on the correction factors, but I think we're also years away from that being the primary uncertainty we face.
Okay, thanks.
Victoria?
Hey, hey, Patrick, thank you for your talk. I was wondering if your slides will be available somewhere.
Sure, I can make them available if you guys like.
Okay, yeah, thank you. And well, I have like a bunch of questions related with your second, yeah, sorry, with your second part of your talk. So, and also a little bit link with the previous question about the radioactivity corrections.
Okay.
So, do you know, or can you estimate more or less if you are sensitive to the B term contribution to these radiative corrections? I mean, this is mostly related with the beta spectrum, right? So if you are able to determine quite precisely the beta spectrum from your beta decay, do you
Sure.
Do you have like an estimation about this precision, probably?
Of how the radiative term affects the half-life?
Actually, I was wondering, yeah, more the angular correlation measurements.
Oh, well,
yeah,
we've already just started looking at that because we haven't actually built the trap yet.
Okay. Okay.
So
yeah.
I assume it's going to be a significant function we have to work out. But right now, my brain's filled with technical details like how can we get our vacuum to be at the -7 level the whole time, or how do we transport the ions without losing transmission? So
yeah, it's quite challenging because also I think you have to control the size of the ion cloud.
Yeah,
so
you have to confine it, because if it gets too big, then you don't have your angular reconstruction as precise as you need, right?
Okay, so sensitivity about your silicon detectors, do you know how much can you reach in this part?
Certainly, that depends on how far back we go, right? The position resolution we can certainly do to the millimeter level. That's been done many times. We might try to do a little more precise than that, but I think millimeter level is something we can sort of buy off the shelf from Micron Semiconductor or some other company.
Okay.
But if we want to improve our angular resolution, which is the thing you really want, we could just go a little bit further away. But we think that a millimeter precision with our nominal distance of, I think, a foot or two, but I think it's probably going to be sufficient.
Okay, probably last question. Do you have already candidates, or I will say it's the proof of experiment?
Already candidate for the first experiment?
Benedict is called, I think.
Sorry, there was some other background. I missed
the isotopes, candidates isotopes for your future experiment. Do you
sure.
have?
We'd probably like to do all of these. So just the red ones in particular, the ones we can make with relatively high degree of precision. We'll probably start with 15 oxygen or 17 fluorine, as those are beams we've made so many times that we really understand them well, and the beams themselves are generally very pure. So we'll probably start with those beams as we try to understand our detector. But we're planning to measure just as many as we can, because for every one you measure, that's another extraction of EUD we can then use to refine our determination.
Okay, yeah, thank you.
Sure.
More questions, comments? Angel again? please. You need to reactivate your microphone.
Yes. Yes.
Okay.
He's just
Now?
waving.
Okay. Okay. Now.
Yes.
I said that I have a question. I mean, link with the last question that Victoria made about. I mean, well, what you show here, the candidates. So I can see that in the program for the astrophysical studies of novae. Okay, you have. I mean, it's not the point of this slide, but okay, you have been studying some isotopes for studying reactions relevant in novae.
Sure.
But what about supernova? I mean, can you reach higher in mass in the production of your facility? I mean, something like A50, A40 something.
So there are some
Like
studies.
magnesium, like vanadium, like.
There are some groups at Notre Dame that occasionally do one or two kinds of measurements that are related to supernova, but the Notre Dame sort of focuses on lower energy nuclear physics, and to get to these higher masses, especially with TwinSol, higher mass radioactive beams, it's much more challenging with energy range of our tandem. Really, the 41 scandium that we have is really pushing the limits of what we could possibly do with the accelerator we have at the moment. So as far as radioactive beams go, this is probably our full range.
Okay.
So doing something with supernova, we're getting up to the n equal 58 or n equal 128 sort of range. That's going to be much harder for us.
Okay. Thank you. Thank you.
More questions, comments? Somebody else? Okay, it seems not. If
We've
not,
tortured him enough.
I think it's a no. Well, I have to say thanks again to Patrick O'Malley for this nice talk and all this answering for the questions. Thank you very much from the side of the director of Physics Institute that cannot attend, but and thank you from the side of the nuclear people that from Mexico, that most of them are now connected. I'm happy to see all of them. And well, thank you very much, Patrick. Thank you very much to everybody, and see you the next time.
Thank you for having me. Bye, guys.
Thank you. Thank you. Thank you very much.
Thank you.
Nice to see you. Thank you very much for everybody.
Yeah, nice to see you.
I hope to see you soon.
And, ojalá que las transparencias sí se puedan conseguir.